This is one of our seminars in the series, and today, the 27th of May 2025, we are going to listen to one of us, our own person, Christian Eze. Christian Eze is a lecturer at the Department of Physics and Astronomy, University of Nigeria, Nsukka. But he's currently on a doctoral research at Nicholas Copernicus Astronomical Center in Warsaw, Poland. And Christian is a widely connected, I think he's now on a research visit to National Science Center somewhere in Belgium. So he's going to talk to us today on a title, Cosmic Symphony, a dive into the asteroseismic world of pulsating massive eclipsing binaries. So I think he's working on massive binary stars. And today we are going to listen to him and get more knowledge about what these pulsating massive binaries are and the phenomena around it. So Christian, over to you.
Thank you, Prof.
For about 1 hour, and then we will interact with you by way of questions and clarifications. Thank you.
Okay. Thank you, Prof, for the introduction. Let me share my screen. Can you see my screen now?
Yes.
Okay. Okay, just like a prof already said, my name is Christian Ikechukwueze, and I'm a lecturer at the Department of Physics and Astronomy at University of Nigeria, Nsukka. Also a doctoral researcher at Nicholas Copernicus Astronomical Center in Warsaw, Poland. And currently I'm a doctoral research intern at KU Leuven in Belgium. I want to actually acknowledge two of the funding agencies, National Science Center, that is funding my doctoral research, led by under the NCN Opus grant, led by Professor Gerard Handler. And I also want to acknowledge the Polish National Agency for Academic Exchange for funding the doctoral research intern. For funding the doctoral research internship. Today, I'll be talking about Cosmic Symphony, a dive into the astroseismic world of pulsating massive eclipsing binaries. I will try as much as possible to present this talk without boring you much with equations and much technicalities. Okay, if you look at this, you see a guitar and a star. And moving from what we already know, if you pluck the string of a guitar, you notice that it vibrates. And while it vibrates, the body of the guitar also vibrates. So this causes the resonance of the body at a natural frequency. And this resonance shapes and amplifies the sound that you hear. In the same vein, the star, especially the pulsating stars, also vibrate or oscillate at their eigenfrequencies. And we'll be seeing later in the talk how some of these things happen. Then what is astroseismology? Astroseismology is the study of the interior of stars using their oscillations. Is actually gotten from just like the seismic distance you are studying here on Earth. But in this case, we are studying stars using the stellar oscillations. And these oscillations can come in two forms. It can come in radial form or non-radial oscillations. And in radial forms, you notice that the star expands and shrinks periodically in such a way that the symmetry of the shape is preserved. So if you are dealing with a spherical star, for instance, then it's expanding and shrinking periodically, and the shape remains intact. We see this type of oscillation in Cepheids, mirrors, and so on, and we use that in the determination of cosmic distances or whatever. Then, if you talk about non-radial oscillation, in that case, the different parts of the star oscillate differently. And then, because they oscillate differently, the symmetry of the shape is not preserved. You have different parts oscillating differently. And this is actually where my research area is focused. Then in these non-radial positions, we have 3 different modes that you can identify from there. And these modes are actually named according to the restoring force that restores the star to its equilibrium position after the excitation of the modes. And the next slide, we'll be talking about excitation. Okay, in the following slides, we'll be talking about excitation. So these P modes are actually acoustic waves or sound waves, if you may use that word, that are usually seen in the envelope of stars. And the G modes are gravity waves that are seen in the interior of stars. The P mode, which is normally called pressure mode, is called pressure mode because the restoring force is pressure, and the gravity mode, the restoring force is gravity. So if you look at this figure by the left, you notice all these lines. You can see my cursor. All these lines are acoustic waves in the envelope, and they are P modes. And the red lines in the interior are the gravity modes. So sometimes a star may have pressure mode in the envelope and gravity mode in the interior, and then you call it mixed mode, situation where you observe both the P mode and the G mode. And then when you observe these modes, you characterize them by the frequency of the mode, the amplitude, and the node. These things will actually talk more about them as we progress. And like we said during the introduction, that's the topic of the topic, that we are dealing with massive pulsators. Massive pulsators here, we'll be talking about the slowly pulsating binaries, SPB, and the beta Cepheid pulsators, so which we call beta Cep. So these SPBs are high mass stars ranging from masses of 2 to 7 solar masses, and beta Cep pulsators are high mass stars ranging from 7 to 25 solar masses. My work is actually centered on beta Cep pulsators. So what actually causes oscillations in stars? Maybe we can start from the star closest to us, which is the sun. And the sun is just a small sized star, which has a radiative core and a convective envelope. And then sometimes the turbulent convection in the convective envelope will excite random oscillations in the star. And that's why we say that in stars, in the sun, we say that in the sun, the oscillation is stochastically excited by turbulent convection in the convective layer of the sun. Then when you go to other stars, you begin to talk about the heat engine or opacity mechanism. So if you talk about opacity, what we are dealing with is a situation where the different layers in the star are opaque to different elements. So you have different partial ionization layers that are opaque to heat at different levels. So because they are opaque to heat, they trap heat at that particular layer. And if the heat is trapped, that place is contracting as the heat is being trapped. And at some point, the contraction causes a distortion in the equilibrium configuration, and that place releases the heat and expands beyond the equilibrium configuration. So this contraction and expansion within that layer causes a kind of oscillation that you observe as pulsations. And in the case of massive star, the oscillations are opacity driven by what is happening in the ion group partial ionization layers. And like I said previously, the restoring forces have already talked about the modes and then how they are named according to the restoring forces. Then we also have the tidal effects. That's where you have tidally excited oscillations. This was talked in detail. It was discussed in detail during the last seminar where the person talked about tidally excited oscillations. So I won't be talking about that again. Then how do we observe these things as astronomers? The first thing we do is to conduct maybe photometric observation. In this case, we are using space-based observation from Kepler, K2, and TESS. TESS is Transit Exoplanet Survey Satellites. Of course, it was designed for exoplanets, but the complementary sciences include astroseismology and others. So what we do is that we use this telescope, observe a particular star in this particular field, and then from the pixel, you extract the pixel that is connected to that particular star, and you extract the light curve. The light curve is just a plot of the flux against the time. So it's a time series observation. And if you check this, where my pointer is, that's the figure by the right upper panel, you see a light curve of one of our targets. Then when you have this light curve, the next step is to convert this time series data into frequency domain by conducting a Fourier transform. What the Fourier transform does is just to convert the time series into a Fourier domain. And within this Fourier domain, you can see some signatures of positions. This is a beta set position. You can see signatures here, which can be as a result of binarity or maybe SPB positions, gravity mode positions. So what we do is that we try to remove the effect of binarity from this light curve and then get the independent positions from them. And the lower panel gives you a plot where we have already removed the effect of binarity, and then we zoomed in into a section containing some beta set positions. Then sometimes, because these stars are located in dense fields, some of the positions you think belong to them may be coming from nearby stars. And then what we do is to, first of all, after identifying those positions and correcting for blends and all that, we also try to localize the position to a particular star using some instruments. This is also part of the deblending that we do. Then here we have a Doppler map showing the positions of stars. And if you look at this Doppler map, some regions are red, some are blue. And the regions that are blue are actually blue shifted, they are expanding towards you. And the regions that are red are red shifted, which means they're expanding away from you. And how do we get this Doppler map? We get it by characterizing the frequencies we get from the star. And we characterize this frequency by identifying a set of integers, L, M, and N. And this L is the spherical degree, which defines the number of lines on the surface of the star. like these lines, if you can follow my cursor, then this denotes a spherical degree. Then we also have M, which is the azimuthal order, and it defines the lines crossing the equatorial axis. So this white line that goes from, as if it's going from north to south, crossing the equatorial axis, is defined as M. And you have N, which is the radial overtone, that defines a position in the star where there is no oscillation. So with this, if you are able to identify L and M, and probably N from theoretical models, then you'll be able to tell the exact properties of position properties of the star. Then talking about massive stars, you know, previously when I talked about the sun, I told you that the sun has a radiative core and convective envelope. But that's not the case with massive stars. Massive stars have convective core and radiative envelope. And there is a boundary layer between the convective core and the radiative envelope, which we call the convective boundary layer. So in this convective boundary layer, a lot of things are happening. There is a lot of mixing, chemical mixing, and mixing of heat and all that. And this mixing imparts the measurement of both the mass of the star and the core mass. So because of that measurement, if its effect in the measurement of the core mass, then in most cases, people report masses of the stars that are not exactly the same with what is predicted. And that is what leads to what we call the mass discrepancy. So this mass discrepancy is a situation where the mass we get from model-independent procedures like spectroscopy, binary modeling, are different from the masses we derive from the evolutionary models. And this mass discrepancy is believed to be caused by the underestimation of the convective core masses. So, and like I have already said, this underestimation is usually caused by the inaccurate parameterization within this convective boundary region. So what my main doctoral research is focused on is to try to resolve this particular problem, or if not completely resolved, improve our understanding of what is happening there. Then we also have, apart from this mixing, we also have other applications of astroseismology. You can use it to study angular momentum transport. You can use it to study interior rotation. You can use it to study magnetism or magnetic field. And I've already pointed out that you can use it to study interior mixing. Then what do we actually do in astroseismology? This is a snapshot of the methodologies. First, you take a time series observation. Like I said, in our case, we use test data. And then you try to get the frequencies from that system, from that time series data. You identify the modes. When I talk about identifying the modes, I'm talking about identifying, of course, if you get this frequency, you already have the frequency and the amplitude. And then in identifying the modes, using those frequency and amplitude, you will be able to also characterize the modes to get the L, M, and in some occasions, N. And then with these things, you get the observed position properties of that mode. Then you go to the other parts, and then you try to get the stellar parameters. These stellar parameters you can get from spectroscopy, you can get from binary modeling, you can get maybe from cluster, through cluster studies. And in our case, because we are dealing with eclipsing binary, so we intend to get the absolute parameters from binary models. But before doing that, you have to first of all get spectroscopic parameters to be able to even do binary modeling. And then using these observed properties we are getting from these systems, you build stellar models using specific input physics, and then you get the theoretical models, theoretical position models. So you do a statistical analysis of either using chi-square minimization or Bayesian, whatever approach you want, to match the theoretical modes with the observed modes. But then where things get complicated, a lot complicated, is within this region where you have to build the models, because each of the system determines what input physics you use. If you are dealing with a detached system, that's systems where the two components are detached, then you know that you are just dealing with modes only. So you, in your model, you will just be incorporating the mixing and all that. But if you are dealing with a fast rotator, then you have to include Coriolis force, or include rotation in your model. And if you are dealing with maybe a close binary, maybe contact binary or semi-detached binary, you will be thinking that, of course, there should be effect of tide, and you have to include tidal forces. Then if the system is magnetic, you also have to include magnetic field. And all these things, as we include them, the system become more complicated. So the simplest case, of course, is when you just have a detached system. We say simplest because that's the simplest among other scenarios. Then this is the figure on the right. I'll be talking about the beta cell positors here, at least the ones we know till present. Prior to this research that was published in 2024, we only had about less than 25 beta cell positors in eclipsing binaries, known beta cell positors in eclipsing binaries. And with this few number of systems, you won't be able to do a lot in terms of population analysis or symbol astroseismology. So our first step was to, first of all, search for beta cell positors in eclipsing binaries, where we used over 8,000 targets from observed with tests. And then we were able to discover a total of 78 beta cell positors. So among these 78, 59 were new discoveries. And this plot on the right is a HR diagram, a Hertzsprung-Russell diagram, showing they confirmed the candidates beta cell and the beta cell in ellipsoidal variables. So if you check this, the HR diagram, this bold line, dark line, is the line denoting the zero-age main sequence. And then it keeps moving. You have the instability strip within this region. So, and if you talk about the figure on the left, you are talking about the general classification of systems that show positions. So this is an astroseismic HR diagram. So what we did here is just only talking about these two regions, which is SPB and beta cell, is only discussing this once. These other ones are other set of systems with some other experts in them. But what this figure shows are the different pulsating systems that we see. There are solar-like oscillators here with maybe 1 solar mass to up to roughly 1.5 solar mass. And along this instability strip here, you have the radial positors, the Cepheids, the RR Lares, and so on. Then I said previously that we conduct spectroscopic follow-up to get some parameters that we actually need to do further studies, because in most cases, you don't do astroseismology in isolation. You do it you get other complementary science from spectroscopy or binary models or cluster, because you need the stellar parameters first to be able to even talk about going into the interior. So in this spectroscopic follow-up, our aim is to characterize the orbital variability, get the orbital elements and all that. And I'll start first with describing what happens if you're observing an eclipsing binary. So if you look at this figure on the right upper panel, if you can see my cursor, then you notice that if an observer is here, let's assume that this observer is the telescope, for instance, here on Earth, and then you see this system, A and B, they are orbiting around a common center. Then when these two systems are aligned, then you have this type of signatures in the spectra. You just have a common line in the spectra. Then, but if they keep moving, and at some point they are aligned in such a way that one is coming towards you, the other one is going away from you, the one that is coming towards you is blue shifted towards you, and the one that is going away is red shifted. And that is what you see here, that this one, which is A now, the arrow pointing here, is blue shifted, and then this one is red shifted. And with this, you can actually get the Doppler shift in this. So when you observe this type of things, they can leave imprints in the spectra here. This is the observed spectra where you have the flux and the wavelength. And then we try to use some processes to extract the radial velocities from this spectra and then fit the radial velocity semi-amplitudes to get the orbital elements. I won't bore you with details of how to do this, but this is just a sample of the radial velocity fits in one of our systems. Then, and in observations, we conducted observations with some telescopes like SOTS, Chiron, that's spectra, Chiron spectrograph. We also conducted observations with HEMS, and Skenet Place Observatory. Then, unlike single stars, where you can just get maybe the atmospheric parameters from those spectra directly, or single-lined spectroscopic binaries where you can get it directly. In double-line spectroscopic binary, what you observe in the spectra is the net effect of the two components. So if you want to get the atmospheric solutions of any of the components, what you have to do first is to disentangle the spectra, and that is what we did in this, for instance, using FD3 binary. So when you disentangle the spectra, you can do some analysis by maybe cross-matching the observed disentangled spectra with a synthetic spectrum using maybe H alpha lines or H beta lines or gamma lines, depending on the ones that are available in your spectra. And then the helium lines, you can determine the effective temperature, the log G and V sin I. There are a lot of other things that you can actually determine from a spectra, but in our case, our interests are mostly effective temperature, log G and V sin I, and in some occasion, metallicity. Then when you get the orbital parameters or orbital elements from the spectra, you can actually proceed to fitting the binary models. And in fitting the binary models, if you intend to get the absolute parameters, you may in most cases fit jointly the light curve and the radial velocity curve. And then from there, you can derive the absolute parameters like mass, radius, and so on. Then here is one of our systems where we fitted a model to the light curve to derive the absolute parameters. And this is a post-mass transfer system. Post-mass transfer in the sense that there was signatures of mass transfer in the past. Maybe in a binary system, for instance, you may assume that the primary is bigger and the secondary is smaller or whatever. But maybe in the past, the secondary was bigger and then the primary was smaller. But there was a case of mass transfer where the current primary now gained more mass from the secondary and eventually becomes bigger than the secondary at its stance. And if you look at this, there is a flux excess around this region, which is believed that maybe some fragments of the mass transfer blocked some fluxes coming from that system. And then you're able to see a situation where the model has excess flux than the actual observed light curve. Then we talk about here the different scenarios, like I talked about the applications earlier, where we talk about interior rotation. So if you have interior rotation in a system, you will be able to see the signatures in your positions. And then if you see the signatures in your positions, you will be able to know that since I have this in my position, I should be able to incorporate rotation in the model that I'm building. And here is a sample of rotational splitting. There are two likely signatures. If you are using spectroscopy, when the V sin I is so high, you begin to suspect that this may be a fast rotator. And then when you get to positions, you check the frequency and see if there is effect of rotation in that position. And looking at this, for instance, you see this central frequency, and then you see other independent position frequencies that are almost equidistant from this. Of course, in some cases, you do experience asymmetric splitting. And if you are to plot this spacing, that is the spacing between each of these frequencies against the period, then you see a plot that is damped in this form. That is a signature of rotation in the system. If it is just following horizontally this way, an undamped system, then you notice that this is not rotation. And if you look at this, you see that this one is split in periods. That is, you have spacing in periods. This is usually seen in P modes. As we progress, it's usually seen in G modes. As we progress, you will see the ones that we see in P modes. And on the right, you see a figure here, which discusses the effect of rotation in the position frequency or the effect of magnetism in the position frequency. In this one, you have just rotational splitting, which can be symmetric. And in some occasions, you can still see asymmetric rotational splitting. But if you see this down one, you see that you have asymmetry. And the one with smaller spacing is on the left-hand side. That is magnetic effects. If you have asymmetry and the one with smaller spacing is on the right-hand side, what is causing it is not magnetism, but still rotation. So rotation you can have symmetric splitting, you can still have asymmetric splitting. And with this rotational splitting, you can actually infer the position from positions in a system. So in this one, in one of our systems, which is a beta set that is usually having P modes, then we have a spacing in frequency and not in period in this case. In G mode, you have spacing in period. And with that spacing, you can do a lot of other calculations to derive age and all that, but I won't bore you with those details. So, and here we have a shell diagram that shows a curve denoting possible rotation in this system. Then what are the two main approaches that we use to determine modes observationally. Then the first one is rotational splitting, which I've just talked about in the previous slides. And here you see the central distinct. The central, it doesn't necessarily mean that it should be the one with dominant position. Like here, the splitting is within this, this, and then you have this, and this. So you can infer the positions with this splitting. And here we've identified this to be L equal to 2 and M equal to 0 with the multiplets as multipliers of L equal to 2. Then in other case, you can also use multicolor photometry. In our case, we use the SAO multicolor photometry, that is South African Observatory multicolor photometry. And then you try to compute the amplitude ratios from those systems, those multicolor photometry. In a multicolor photometry, you are observing a system with different filters. We use SDSS filters, for instance, which has the U, G, R, I, Z filters. And each of these filters has different response functions. So if you're observing with different filters, you are getting different responses from these different filters. And by the time you finish the observation and analysis, you'll be able to get the amplitude ratios from each of these filters. And then when you plot the amplitude ratio against the wavelengths of the filters, then you will see this black one, that is the observed distance for a particular frequency. And then you overplot it with the theoretical amplitude ratios in that filters. And the position of that thing will be able to tell you what type of module you are dealing with. So in our case, some of our systems that show rotational splitting, we identify modes using this. And in some that we're able to get multicolor photometric data, we identify modes with this. Then in this slide, I'm trying to zoom in into that convective boundary layer that we talked about previously. I told you that the mixing there affects a lot of things. And if you're able to characterize the mixing, then you're able to solve a lot of problems. So here, we discussed the mixing prescriptions, predominantly 3, where we have the convective overshoots, the entrainment, and the penetrative convection. And what we mean in this case, if you have a system where matter or chemical element is mixed from the envelope to the interior, then you call it convective overshoot. In this case, no heat is transferred, is mixed from the radiative envelope to the convective core. Then, but if you have a situation where both heat and chemical elements are mixed, you call it convective penetrative convection. But in some occasions, you have what we call entrainment, because between the boundary of that radiative layer and the convective boundary distinct, you are talking about a star, which is a ball of gas, and you don't expect a laminar flow within this region. So sometimes the flow can be turbulent, and because of this turbulent flow, it scraps portion of that radiative layer into the convective core layer, into the convective layer. And that is what we call entrainment. So this mixings scenario affects what happens in the interior. Remember, if you're adding material from radiative envelope to convective core, what it means is that you are increasing the fuel in the core of the star. And by so doing, you are also increasing the convective core mass because you are increasing the fuel. And even in some sense, you are also likely increasing the main sequence lifetime. So what then do we do with some of this information about mixing prescriptions and all that? This paper by Kachenko et al. 2020, it tried to solve the problem of mass discrepancy using eclipsing binaries. Some people have tried to do that using eclipsing binaries. Some have tried to do it using astroseismology alone. And in what he found, he discovered that increasing the core mixing and maybe incorporating some atmospheric properties like microturbulence will actually reduce the discrepancy by a certain percentage. So they were able to reduce it by about 30% or thereabouts. So, and what I'm trying to show with these two plots here is to tell you how small fractions of these mixing parameters, like overshoots and all that, can impact the stellar properties you infer from whatever thing you are doing. This is log G, which is like surface gravity, and this is the effective temperature. So in this particular plot, you have the effects of convective boundary mixing. And if you look at this, for instance, you notice that we have different overshoots, which this FOV is talking about the convective overshoot that I just discussed in last slide. You have 0.005 here, 0.020, and 0.040. And looking at this, you see how they can significantly alter the log G you are getting from the system. So if you don't get accurate parameterization of these things, you are already getting a model that is not a true representation of what you are dealing with. And in these other plots, you also see how the metallicity and masses, how they also shift the models you are getting. So what my main work is focused on is trying to use the information from these mixing prescriptions and then try to combine the strength of astroseismology and the eclipsing binary modeling to improve on this mass discrepancy resolution techniques. Then this is also another work is still talking about the convective binary mix boundary mixing, but in this case, instead of using overshoots, this person used a time-dependent convective penetration, and he plotted here the level of penetration zone against the mass. And looking at this, you notice that from here, this thing increases as the mass increases. That is because the level of the penetration zone increases as the luminosity or the convective core mass increases. So if the luminosity increases, then you expect maybe likely increase in mass and in core mass. And once you have increase in luminosity and core mass, incidentally, you will be having increase in mass. So because of that, you notice that this thing is increasing with mass. But then within this region, when you consider the hydrogen mass fraction, which is a uniform way of describing what happens about the age, then you notice that here, the higher the hydrogen mass fraction, the lower the what? The penetrative distance. That is why, because if you are moving from main sequence to post-main sequence, then you notice that as the star is growing in age, the core is shrinking because we are losing either hydrogen or the fuel that you are using there, and the envelope is expanding. So in this case, if you have a core mass that is bigger, what is trying to tell the system is that this star is probably in its early phase in the main sequence. If you have a core mass that is shrinking, then it suggests that this thing is already at late evolution stage. And because of this, you notice this type of thing where the higher hydrogen mass fraction gives you a lower penetrative zone. So this person also, in this paper, also compared what he predicted from this with other ones in literature, including the one, the Kachenko et al., the paper of Kachenko et al. That I discussed earlier. And he discovered that there is a systematic difference in the measurements. So that is probably because in his case, he just considered the model, the penetrative convection, whereas in some other cases, the observed penetrative distance is usually including most of, if not all, of the mixing procedure in that observed system. And then what is, I think I'll be rounding off because so what is actually the future of this study? In this particular field, like I said earlier, what we are currently working on is to try to model jointly the binarity and positions using MESA and Jaya with all the observed properties that we've got so far to be able to characterize the interiors of the star by using appropriate mixing prescriptions. Then we are also trying to use, having increased the number of beta cell positors in eclipsing binaries, we're also trying to do ensemble astroseismology. I think recently, this 2025, a paper by Dario here in Leuven with some of the team here, they also conducted ensemble astroseismology using Gaia data. Then there are also recent developments about conducting 3D models of stellar structure and evolution of pulsating variables. In 2022, Anders et al. 2022 actually conducted 2D model, and they were even the one that actually predicted a time dependent penetrative convection, where they assumed that at different layers of the mixing region, that different things happen. It's not just a lump of overshoot that we assign at some point. So if you treat it at different layers as a time-dependent function, you will be able to get something also very meaningful. Then the final thing is the Plato, which is the European Space Agency space mission that will be launched in 2026. Just like TESS is the NASA thing, but this one is owned by ESA and is expected to be launched in 2026. The core science mission is actually studying of exoplanets. But anything that studies exoplanets, in most cases, will give, for you to understand even the exoplanets, you have to understand the parent stars because planets don't exist in isolation. So whenever a mission is talking about exoplanets, the complementary sciences will always involve stars that actually give birth to those planets. For instance, in our solar system, we have the sun as the star, and we have other planets revolving around it. So all those exoplanets also have this thing. And in Plato, for instance, even though the core science is exoplanets, we still have complementary sciences that involve astroseismology and binary modeling and so on. So I'll stop here. Thank you for listening.
Yeah, thank you so much, Christian, for the awesome presentation. I think it's now time for comments, questions, and some clarifications. However, before you end this seminar, Christian, I would want you to give us some more information about your center and the opportunities that there could be for some of our younger colleagues. So I think that will be a welcome idea if you'll be able to do that. And I'm also happy that the general coordinator of our project, Professor Fulvio, is there, seated since the beginning of this program. I think before you leave, because we usually leave before the end of the program. Before you leave, please say hi to our colleagues that have consistently shown interest in this seminar series, and I have been seeing their faces each time where we present this seminar. So I think the floor is open for whoever that has questions or some comments. My first question I want to ask is this eclipsing binaries, or rather pulsating massive eclipsing binaries, does it have anything to do with the so-called pulsars we have been studying in astrophysics? Is it the same mechanism that produced the pulsation? Yeah, just give us a little link between this and the normal pulsars we have been studying in astrophysics. Thank
Okay.
you.
First, let me start with the first thing that you requested. In my center, Nicholas Copernicus Astronomical Center in Warsaw, they actually advertise. In fact, you can get virtually everything you study in astronomy in that center. People from black holes, gravitational waves, astroseismology, neutron stars, and so on. So they usually advertise their openings on their website, and in some occasions they also include it in AS job register. I think currently, if I'm not mistaken, there may be an opening there on the website. So if you're interested in joining the place, you can also look up the website. Also here in KU Leuven is also another vibrant institution. The Institute of Astronomy here is very large with so many PhD and postdocs, as well as many researchers here present. So if you're interested in any of them, they mostly advertise the openings in their website as well as AS job register. Then talking about pulsars, one, I will have to let you know that neutrons, what I'm studying now, are actually neutron star progenitors. Massive stars of masses between 7 to 25 solar masses. When they die, the remnants is actually neutron star. So, but the position we are talking about here is intrinsic, unlike the extrinsic position that we see in pulsars. Because in pulsars, what we call position is that you are receiving the beam. The beam is just like a lighthouse, like the bossa is rotating, and each time the beam of radiation crosses your path, you call it a pulse. That is extrinsic in nature because the beam is actually just coming from a particular point and then is flashing across your line of sight, and you are receiving it at regular intervals. You call it pulsations. So, but in our case here now, we have what we call pulsation is the intrinsic pulsations within the star itself, not necessarily what we see like the observation in pulsar. And again, if you are observing, of course, I have to point out that some people are still currently searching to know if they will be able to observe intrinsic pulsations in pulsar. At the moment, I don't know if there's been a breakthrough in that, but the pulsation we are talking about in astroseismology is a bit different from what you see in pulsars, which actually is a kind of just receiving the pulse, the beaming from the pulsar. I don't know if you...
Yeah, I think you answered my question.
And to
Thank
add
you.
to that, in most cases, we studied pulsar in radio domain, but here this is in entirely optical domain. Of course, there are still people that study neutron star in optical domain, and it depends on their science goal. So they can, even some also study it in X-rays. So it depends on the science goal.
Okay, thank you.
Yeah, I don't usually see people raising hand or whatever. So maybe you can just coordinate and...
Aman was raising hand.
Okay.
Aman, are you still there?
Yes.
Good. On with
My
your
first
comment.
question, which I wanted to ask, was I didn't understand the part of the slide for the last 10 minutes. So could you like explain that in brief again? Because I really didn't understand in detail, just to summarize.
Sorry, I didn't get your question. The part of
My
what?
my question was the slides after the one where you said the initial metallicity and the variations are the slides after that slide. I didn't really understand what was that. So could you like explain what they're about in brief, please?
Okay.
Yeah.
The slide after that of metallicity, I think so.
Is it this?
Yeah, after this one. After this one. After.
Just tell me if you get, if you remember the number of slide, I can.
It's after this one. It's I think it's slide 15.
Okay.
Let's see. 15 or 16.
Yeah.
Yeah, 17.
Good.
Is it this
18.
one?
No, it's 18. No,
Okay.
19. It's 19.
Okay, that should be this one because this is my
Yes.
last listing.
Okay.
Yes, this one. Yeah, I
Okay.
didn't understand that.
Okay. If you look at this from here, you already notice some boundary regions here because they are defined. You have the overshoots region, you have penetrative zone. Then what that particular thing is doing is to evaluate the dependence of the extent of the penetration on mass. So what it's trying to tell you is if you have a system of different masses, and then you are trying to infer how the chemical elements as well as heat would be moving from the radiative envelope to the core, how do they depend on the mass? So, and looking at these plots, what is the first thing you will notice is that the predicted penetrative region actually increases with mass. There is a sharp peak around here. And beyond this sharp peak, you have a monotonic increase from here. So which tells you that here you have this increasing as the mass increases. And why do we expect that type of thing? We expect it because this convective penetration is affected by the luminosity, is affected by convective core mass, is affected by rate of diffusion and whatever in that region. And then if you have an increasing luminosity as well as increasing core mass, then what it implies is that you will definitely have increasing mass because these are correlated. For you to have a higher core mass, it's likely you have a higher mass. So that thing, the first thing you observe is that this is increasing with mass. And then another thing that you also observe from this figure, because this predicted one is coded in color. What you plotted here is three things. The first one is the dependence of this convective penetration zone against the mass. And the second one is its dependence against the hydrogen mass fraction. So if you notice this hydrogen mass fraction, you notice that this color has the highest hydrogen mass fraction, and this place color has the lowest hydrogen mass fraction. So when you zoom into this region where there is a significant difference in them, you will notice this. Can you see my cursor, right? You can see my cursor.
I can see it.
Okay, so you notice this particular region that is zoomed in here, and then you notice that instead of increasing this convective penetration increasing with increasing hydrogen mass fraction, it is actually decreasing with it, because this one is 0.65 and it is the lowest. Why this one hydrogen mass fraction that is lowest is the highest here? Why do we see that type of trend? We see that type of trend because this hydrogen mass fraction is a way of defining the age from the model, not necessarily the age directly, but it's something that uniformly defines age. So what it tells you is that if a star is evolving, we can start from the zero age main sequence, for instance. As it is evolving, it is burning the fuel in the core. And as it is burning the fuel in the core, the core is shrinking, reducing both the core mass and size, and the envelope is expanding. So if the core is shrinking, what it implies is that the hydrogen mass fraction will be getting smaller and smaller. And that tells you that this thing keeps getting smaller and smaller as the star ages. So you start noticing that because the star is aging and hydrogen mass fraction is representing a function of the age, then the penetration will be decreasing with it, even though the penetration increases with mass. And then the final thing that is represented in this plot is a comparison of this predicted penetrative convection with other observed mixing reported in literature. And they notice that there is a systematic difference, because if you notice here, this one moved here, but this one actually moved up and actually had a bend around here. So what causes this systematic difference? What actually causes it is maybe a likely difference in the mixing that were incorporated in all this. In this particular one, the person considered only convective penetration. In this other one, even though they considered convective penetration, because it's an observed distance, there could be other mixing prescription that have been accounted in these observed properties. And that is why you see a systematic difference in them. So we have identified three things in this particular figure: the dependence of penetration on mass, the dependence on hydrogen mass fraction, and the comparison of the predicted penetration with some other observed mixing prescriptions. Is that clear now?
What does the acronym CBM mean?
CBM is convective boundary mixing.
Oh, okay.
That was what I just...
And cont means
Yeah, that's
concentration, right?
continue. Because we started from this here. We started talking about mixing from here.
Yes, because why I asked this, because I had a network problem which cut me off. That's why I wasn't able to understand the last slide.
Okay, that's fine.
Yes, and the back to the first slide. What does SBD mean? The first slide. You said there's a B center stars and then the SB.
The first slide, we have SPB, which is slowly pulsating binary, is a class of massive star, massive pulsator, which has masses ranging from maybe 2 solar masses to about 7 solar masses. And then they have pulsation periods ranging in hours to maybe a day or few days. But this beta cell pulsator is another class of massive star, massive pulsator, that have short pulsation periods of maybe 6 to 12 hours, and they have masses ranging from 7 to 25 solar masses. And the beta cell pulsators usually have pressure mode, and in some occasions G mode, and even mixed mode. But SPB particularly only have gravity modes. So in SPB, you only have gravity modes. And like I already pointed out, gravity mode are mostly seen in the interior, why pressure modes are seen in the envelope of the star.
And are the examples of those two types of stars like SPB and B center B?
Sorry, would you repeat your question?
What is an example of SPB stars?
Okay. One of the example is this thing I wrote here, this particular HD 329379. I use this as an example here because this star has both beta cell position, which is a frequency. If you have a position period of 6 to 12 hours, it means you have a frequency of about 3 to maybe let me just say above 3 cycles per day. And if you look at this region, this is a beta cell position. Is located within this beta cell regime. And that is what we zoomed into here. Then if you look at this other region in the second panel, you have very high distance, which if you zoom into it, or if you converge it, you notice that you have not only SPBs, but you also have harmonics of the orbital frequency. So what we did was to first of all remove the harmonics of the orbital frequency. And once you remove the harmonics of the orbital frequency, all other things you see in the system will either be independent positions or noise. And when we removed it, we saw some other position frequencies here that are beyond the noise limit. So these ones you see here in the lower frequency regime is the SPB, whereas this one is the beta cell positions. But then it's just like saying that the long period positions in massive stars are G modes, which in most cases you see in SPB, and the short period positions are the P modes. Remember, a period is 1 over frequency in your basic physics. So here we are dealing with frequency domain. So if you check reciprocal of this, you'll be able to tell which is short and which is long. So this is one of the examples of SPB.
So is this star a red giant or a blue giant? Is it a red giant or a blue giant? When I meant like an example, that's what I meant. Like, is it red giants? Are red giants a good example of SPBs? And
okay.
like example, like B centers. Is blue giants a good example of that? That's what I meant.
Okay, let me tell you. For instance, I've already told you that this is a good example of hybrid positor showing both beta cell position and the XPB positions. Then secondly, I want to tell you that this is still in the main sequence stage, but what you call red giant is no longer in the main sequence, is already in the post main sequence. Good. If a star is evolving, let's assume that we start evolving the star from the pre-main sequence where you have a those in mass star formation will tell you have a protostar. It keeps on creating matter till it eventually ignites core hydrogen bonding. And then you call that pre-main sequence. And then you start moving from that pre-main sequence into the main sequence. And at the zero-age main sequence, that's when the hydrogen bonding starts or gets ignited. And then as we are moving from that hydrogen bonding, then you'll be using the hydrogen in the shell, in the core. At some point, the hydrogen in the core gets exhausted. You start burning helium in the core. Some point, you start burning hydrogen in the shell and so on until you exhaust all these things. And as these things are happening, the core is shrinking and the envelope is expanding until it gets into the late distance when you must have exhausted the fuel and it evolves into a red giant with some other properties. Some other people are studying astroseismology of red giants. Even some also are studying other supergiants, which is originating from the late evolution stage of high mass stars before eventual collapse through supernova into neutron stars or black hole. So this is not a red giant or a supergiant. This is still within the main sequence.
Yeah. Okay. Thank
I
you,
think
Christian, for that
I wanted to remind Prof that is.
clarification. Yes. We want to end this thing in the next 2-3 minutes. So one hand is up. Let the person just drop his question, and then we can think of how to end. Ugu.
Thank you, Christian, for your impressive presentation. You are really doing a great job. I don't know if you can go back. There is a slide where you have you explain about blue shift and red shift with some angles labeled there.
Okay, yeah.
You have 90. I think the other is like you have fast. Where you have some angles.
Is it this
labeled.
one?
No, there's angles 90, 45, 0.
Oh, okay. This, yeah.
Yes. So I don't know if you can throw more light what the angle there represents and the effect of
Okay.
this don't know its rotation.
Okay. What we see here is trying to tell you that that angle is talking about the inclination of the system. And the visibility of the mode also depends on the inclination. That is what it's trying to tell you. Even though the L and M or L, the parameters are not changing, you will be able to see different behaviors if you study them at different inclination angles. So if I use this central one, for instance, if you can see my cursor where we have L,
Yes.
M equal to 5,2.
Yeah.
In this one, you can visibly understand the M equal to 2 that is defined here. Because you have two lines crossing the equatorial axis. That is this line, 1, and then you have this other line, 2. That is defines this. But if you are dealing with this thing, even though this L and M didn't change, if you're observing it at a different inclination angle, you'll be seeing it differently. So what's happened and what the inclination angle is doing here is to tell you that the mode visibility also depends on the angle at which you're observing the mode, irrespective of whether the mode property is changing or not. So this is just like inclination angle of 0, and then it's as if you're observing it from the head of, that is from the nut of this. So you now see this as if it is flattened, but in reality it's not flat, it's just the signature of the inclination angle of that system. That you have two things inclined, and then your observation of that thing depends on your position and how which area of this thing you are seeing. So that is what the angle incorporates in that place. It's just a way of defining
The viewing angle.
the viewing.
Is it
the mode
like
visibility
related
based.
to face on or and edge on?
You said?
Is it like related to face on view and edge on view? Or is it a different thing?
We should use that in literal terms to explain it.
Yeah.
Okay.
Okay. Thank you. Thank you, Ugu, for your active participation. So I think we have tried for today. And yeah, just as I said, Professor Fulvio is there. And I think it will be good if we can say hi to our participants in this seminar. Professor Fulvio.
Yes, I'm here. Hello, can you see me?
Yes, yes.
Yeah, well, thank you very much for this presentation. And I hope that people in the room learned a lot from Christian. And as you know, I'm a geologist, so I couldn't grasp most of these very high-end topics, but that's the reason why we do this seminar with FAST4Future, And I hope that the people in the room will follow up on what Christian said. And I want to thank you, everyone, for the attending, and especially Professor Finbar for organizing this meeting, and Christian for getting online from Europe, I guess. Thank you, and I hope to see you all at the next monthly FAST4Future seminar.
Good. Thank you, Professor Fulvio, for that. It's a very big encouragement that you are there and talking to us, and we are happy to see you. Yeah, thank you so much. Then to our participants, just look out, you will see our information. Of course, we don't have a permanent date for this because sometimes the presenter may decide to change the date due to some circumstances beyond his control. So, but once we confirm a date, we will let everybody know. And on this note, I thank everyone for being part of this, and I thank Christian especially for making out time to put this seminar together. So next month, we will still have another one. So look out for the information. Thank you so much.
Bye.
Thank you. Bye.